Welcome to lecture number 29 on electrical machines 1, and we have been discussing auto transformer. In fact, we have been comparing auto transformer versus two winding transformer, Recall in the last class I told, because if you want to change transfer a certain amount of kVA from primary source side to the load side, you can at two fixed voltage levels V 1, V 2, you can do that by using either a two winding transformer or also by an auto transformer. Now, therefore, there were now we find that there are two options. I can do the same thing, change the level of voltage from V 1 to V 2 and transmit the same kVA. Now, which one to choose? Two options are there. It looks like either of them can be done, but I told you that if you use an auto transformer, then copper required will be less compared to the copper required in a two winding transformer, always less. So, savings of copper will be can be easily found out subtracting these two, but the point is that this ratio is 1 minus 1 minus A. Copper required in an auto transformer is 1 minus 1 by A, where A is N 1 by N 2. A is N 1 by N 2. And we also showed with some numerical examples that as the turns ratio is close to 1, savings of copper will be more and more, but nonetheless, no matter what is this ratio, either large or small, there will be always savings of copper. Then we argued that if that be the case, then it should be only auto transformer all along. Two winding transformer should not be used. What is the fun? Because you will be always saving copper to transmit same kVA from the source to the load side at two fixed different voltages. Same job can be done by an auto transformer, but there were further issues. Then I told you that look, a two winding transformer is a better option if you require isolation. Some critical load is present, if there is an open circuit on the secondary of the two winding transformer, okay, no problem. At best, at most the load will not get any supply, there ends the matter. But that is not to be the case if an open circuit fault occurs in the N 2 turns, that is common portion of these windings of an auto transformer. Even if it becomes open, primary energized, this voltage, this high voltage may appear across this. Of course, this voltage minus whatever is the drop here, that will appear across the load. Therefore, on the load side there may be a sudden rise of voltage if such a fault, that is open circuit in the secondary, that is in the BC part of the winding takes place, and auto transformer does not provide isolation. Therefore, where isolation is a must, no, two winding transformer should be preferred. I mean, auto transformer should not be used, the loads may be critical. That is why two winding transformer is also there, because it provides that isolation. That is what I told in my last class. Now, the question is then when to use auto transformer? Auto transformers can be used. See, I write this thing, copper required for auto transformer, the previous result only auto transformer is we found 1 minus 1 by A into copper required in 2 winding transformer of same rating. Otherwise, what is the fun of writing this 2 winding transformer? This we have found, and we have observed that savings will be more, savings of copper will be more if A is close to 1. In fact, if A equal to 1, I mean this mathematical expression gives me okay, auto transformer does not require any copper. What does that? That is a critical point, forget about that, but I will use an auto transformer. It simply means that no transformer is necessary, then supply voltage the same voltage you want, but there may be situations when, for example, you want to step down the voltage from 1000 volt to say 900 volt. Here this ratio is close to 1, is not 1000 to 900. In this type of transformation, we find savings of copper will be more. That is what we established here in our last class. Turns ratio close to 4 by 3. Savings of copper required is only 25%. Turns ratio is half. Then that is 2, 1 by 2, and savings of copper is only 50%. So, closer you go to A equal to 1, savings of copper will be more and more. If that be the case, then I will say better go for an auto transformer. That is when this voltage V 1 and this voltage V 2 their orders are nearly same. Transformation ratio, for example, 1000 volt to 900 volt, then savings of copper will be quite large, because for this portion you require thinner wire I 2 minus I 1, and for this you recall this is I 1, this is I 2 and this is I 2 minus I 1. Savings of copper will be much more. But then the problem of isolation still remains. Okay, the problem of isolation you cannot avoid, that is there, but look, if this is of the order of 1000 volt and your load requires 900 volt, and now an open circuit takes place here in the common part of the winding, then the voltage which will be coming across the load, will certainly not be 900 volt, it will shoot up via this path, supply will come here via this path, but that voltage rise will be not too high, because it is already this word of the same order, we must understand that. So, not only the savings of copper will be more, but also isolation is not a big issue in the sense that when this voltage and this voltage are at comparable level, same level, then okay, voltage will shoot up from 900 to at best maximum to 1000 volt, only what percentage of increase it is, 10% is it. Therefore, but imagine I am using an auto transformer 1000 volt to say 100 volt. I want to get 100 volt here, and I have decided I will use an auto transformer. Now, first of all, in this case, this ratio being too high, savings of copper will be there compared to a 2-winding transformer, but savings of copper compared to this configuration will be much less, because A is here 10. So, 1 minus 1 by 10. So, it will be 0.9 only. So, copper required in auto transformer will be 90% of what? Of the copper required for making a 2-winding transformer. But nonetheless, a saving, little saving is there. But here the issue is, if there is a open circuit here, then you see the load side gets connected to this high voltage side. It will not shoot up to 1000 volt, but it may shoot up to 600, 700 volt. Why not 1000 volt? There will be a drop here in this case. But nonetheless, so far as the load on this side is concerned, it will feel that rise in voltage, or the personnel whoever is working here on this side, they might get shock if there is a open circuit takes place here and no isolation is provided by auto transformer. I think you have understood this point. Therefore, for the safety of the personnel who expects always here 100 volt, he will suddenly see, okay, it has gone up to 800 volt. This is dangerous, and also it may be dangerous to the load. Load may not, cannot accept that large voltage. But in this case, okay, 900 volt load, working, whoever is working here 900 volt, it will go up to, he must have taken enough precaution to work at this voltage, right? But voltage will only shoot up a little, maybe by 10%, 5% like that, if there is a open circuit occurs. So, isolation problem when A tends to 1, isolation is not that urgent, is not that urgent. This is one, and second thing is savings of copper is substantial, savings of copper substantial. Whereas, in this case, in this ratio, I will say isolation is urgent, isolation must be provided, under what condition? Open circuit in the common. And secondly, savings of copper is also not very high, savings of copper is little. Savings of copper with respect to whom? With respect to a 2-winding transformer. Therefore, for such a large transformation ratio of voltages, you better go for a 2-winding transformer, where isolation will be there. I think you have understood this point. Okay. So, this is the thing. Okay. Now, before I proceed further, that is, see, to understand what is going on in an auto transformer, so far I have taken an ideal case, that is, transformers are having no leakage impedance, this, that, okay, and so on. Acha, I will just point out one thing, that that suppose in the form of a problem, so that you understand what I am trying to tell. Suppose you have an auto transformer, okay. Here is, and it is stepping down. It could also step up. See, I have done all the derivation assuming it to be stepping down the voltages. Now, the same sort of equation I can write and come to the same conclusion even if it is step up. When the ratio will be high, better do not do it, things like that. Okay. That I leave it as an exercise. Suppose I say that derive whatever things I have done, if I apply a voltage here and secondary voltage is V 2, whether still copper savings, why not copper savings will be there. Anyway, primary and secondary can be interchanged, that way you can always argue. Anyway, that is the thing. Okay. So, you know it is there. So, this is the thing. Now, suppose let me solve one problem, ideal auto transformer. How you should be handling this problem, ideal auto transformer. An example. Numerical problems. So, winding impedances are neglected, core losses are not there. We will discuss this slightly later. Suppose I say it is 400 volt, I will apply here. A problem is given, it is 400 volt, and suppose it is 200 volt, I say. I tell that the transformation ratio is such that 400 to 200 volt, and I say that you have connected an impedance here of value say 10, 30 degree, inductive impedance I have connected Z 2. I ask you to find out, calculate currents in all the branches of the circuit, a very straightforward problem, but you should do it like this. One way of doing this, because this is 200, this is 400 given, otherwise number of turns could have been given. Suppose I say that this is A, this is C, A and AC, suppose I say it is 100. Then immediately I will calculate volt per turn, volt per turn, which will be equal to 400 by 100, 4 volt per turn. And suppose I say that NBC is equal to say 50 turns. Then I will say this voltage VBC must be equal to 4 into 50, that is 200 volt, is not? That is how I got the voltages. Now, I have been asked to calculate currents in all the parts of the auto transformer, and mind you, this is dot, this is dot here. First thing what I can see that I can calculate this current I 2. So, I 2 will be 200, all voltages will be in phase, because same flux links all the voltages, and there is no distinction between V 2 and E 2, no distinction between V 1 and E 1, they are one and the same, and all the voltages are in time phase. Why? Because common flux, all this part of these coils same flux is crossing, only thing number of turns are different. Therefore, I 2 will be taking this voltage in reference, I 2 I will calculate simply like this, and which will be equal to 20 minus 30 degree ampere. I will get I 2. Now, I will argue, as I did in case of a 2 winding ideal transformer, that this is I 2 and this is, so V 2, first I write V 2 is equal to 200 0 degree volt. I 2 is this. Then output power, output complex power is equal to V 2 I 2 star, that is what we will be doing. So, this will be 200 0 degree into I 2 star is 20 plus 30 degree, is not. So, this will be 4000 watt plus 30 degree, that is the output complex power, and this must come in from this input, because there is only one source of power where I am feeding supply 400 volt AC, RMS value is 400 volt. Therefore, if I assume this current to be I 1, which is still now unknown, I will say, and mind you V 2 is this, therefore, V 1 is also known, 400 0 degree, but I do not know I 1. So, what I will do is, I will say that V 1 I 1 star must be equal to V 2 I 2 star. Whatever you dump on the load must be drawn in from this source side, this is source. It must be like that. Therefore, I 1 star will be equal to V 2 I 2 star. V 2 I 2 star is this. So, I put those 4000 30 degree divided by V 1, which is 400 0 degree, and this becomes how much? 10 ampere, 10 30 degree. But mind you, this is I 1 star, therefore, I 1 will be 10 minus 30 degree. Therefore, balancing the power on the load side, and that is the power drawn from the source, you can avoid several physical things what is going on. That is, I know I 1 now. The moment I know I 1, then I can calculate this current. This current better show in this way, this current, then will be I 2 minus I 1. That is how we are specifying. I 2 is known, I 1 is known. Therefore, current in this portion, in this direction, it can be calculated. So, I 2 was here, there is no star. So, 20 minus 30 degree minus I 1, which is 10 minus 30 degree, whatever it comes. So, the current distribution of various parts of this circuit can be easily calculated, provided of course, the transformer is ideal. Winding resistances are not there, leakage reactances are not there, such that V 1 becomes C 1, V 2 becomes C 2, and so on. Another example I will ask you to do is this one. Suppose you have same problem sort of thing. Suppose here I have applied 400 volt, 50 hertz. Okay. And once again I say that NAC is equal to 100 NAC. Then immediately I will calculate volt per turn is 400 by 100 is equal to 4. Okay. Now, what I am doing is I am taking a tapping from point B such that N B C is equal to suppose 75. Therefore, I will immediately calculate V B C, voltage available between these two is this was 4. So, 4 into 75, that is 300 volt I will be getting. And suppose I have two loads, so one requires 300 volt supply, another requires 200 volt supply. So, from the same sort of auto transformer, suppose you have another tapping say at point D such that N DC I say it is 50. Then therefore, V DC will be equal to 50 into 4 is equal to 200 volt. And mind you, all these voltages are in phase. This is 0 degree, this is 0 degree, and your supply voltage VAC is the supply, that is also 400 volt 0 degree, is not? That is the thing. Now, I say that I will connect here load. So, here you will get 200 volt and here you will get 300 volt. And suppose 200 volt I terminate it on a load whose impedance is say 10 30 degree ohm like the previous one, and between these 2 points I supply another load. Where you are getting this, and suppose I connect here an impedance of 30 minus 30 degree like this. That is from the same auto transformer by 2 tappings at B and D, C being the common terminals, I will supply 2 loads which requires 2 different voltage levels. Then the question is this: show the current distribution in various parts of the coils and this way. One way of doing this is going by physical argument, trying to balance the MMFs, but there is a shortcut method. What is that? This is the only source of input power and power are consumed only here and there, transformer being ideal. So, these two much match. So, this is your V 1 supply voltage. Therefore, I will first say that let this be I 2, let this be I 3 and let this be I 1. So, I will say that V 1 I 1 star total complex power absorbed by through the terminals AC is V 1 I 1 star must be equal to, suppose this I say as V 2 must be equal to V 2 I 2 star plus V d c, suppose I call it as V 3, V 3 I 3 star. This is the thing, and I 2 and I 3 are known. What will be I 2? I 2 will be B 2, that is 300 0 degree divided by 30 minus 30, it is capacitive loading, and this will come out to be 10 plus 30 degree, and I 3 will become 200 0 degree divided by 10 minus 30, 10 plus 30, if you do, it will become 20 minus 30. B 2, B 3, of course, if this is I 2, then do not forget to calculate I 2 star, that is 10 minus 30 degree. If this is I 3, calculate I 3 star, which will be equal to 20 plus 30 degree ampere. Put it here, everything is known including V 1. Then you calculate I 1 star, which I am not going to calculate, put the values, all are phasors, plus V 3 I 3 star divided by V 1. Of course, after getting this, I 1 will be equal to I 1 star star, another complex. Do not forget to take this complex conjugate. Anyway, this is how, no matter how many tappings you have taken, what different kinds of load you have connected, very easily it can be done. And after I get this I 1, I 2, after I get I 1, I 2, all the things, what I will do? I will go on applying this KCL here at B, and also do not forget about this way or that way, it does not matter. So far you are correctly writing the KCL, you can show this current to be I 1 minus I 2, I 1 coming, I 2 going, I 1 minus I 2. Here I 1 minus I 2 coming, then another I 3 is going, I 1 minus I 2 minus I 3. Interesting thing you will observe, the MMF of this portion, whatever turns AB, MMF, these are the isolated coils, this portion, this portion, this portion. So, sum of this MMF will vanish to 0, it will be automatically taken care of. Anyway, we will continue with this next class. Thank you.